Okay, so just handed back the homeworks, and I don't think today is a homework today, right?
No.
In fact, the thing that we need to announce is that we have an exam on Thursday, is that right?
Are you reviewing today?
Well, that's the other thing I was going to let you know. Here's the thing. First of all, you know, the material is just so straightforward. I'm not sure that.
We can at least run through
Can
and
we
see
point
what.
out?
Let me show.
Tables you said we had to have memorized.
Yes, let me go through and tell you what I expect you to know on the exam. But then, in terms of reviewing, I mean, it's all just fairly straightforward. I mean, I don't think that we have to spend. Plus, there is an assignment due on Monday
With this stuff.
with new stuff that's not going to be on the exam, but I would like to go over that material today. So I know students generally do not like to have your minds cluttered with information that's not going to be on the exam, but we'll just have to suck it up
Alright.
and persevere, because we really do need to go through some new material, even though it's not going to be on the exam for Thursday. Okay, so here's what we did. Here's what. First of all, we reviewed some concepts and levels of abstraction. So obviously, you need to know. Actually, I've told you just about pretty much everything as we've gone through this material. What I expect you to know. And so remember, one of the things was the 7 levels of abstraction and the concept of abstraction. What are the 3 kinds of diagrams that illustrate
Level.
abstraction?
Oh, wow.
Level, nesting, and hierarchy.
Level diagram, nesting diagram, and see, level, nesting, and then what was the other one?
Hierarchy.
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 Yeah. So you know how those work, and then so you know the 7 levels. What are the 7 levels?
App 7.
App 7, HOL 6,
Assembly.
Assembly 5,
Operating.
Operating System 4,
ISA 3,
ISA 3,
microcode,
Microcode 2,
logic gate.
Logic Gate 1. And then we reviewed C++, and what's the big deal with the C++ memory model?
Global variables.
Global variables are stored where?
Fixed location.
Fixed location in memory,
Local variables
Stored
on the stack.
on the stack,
On the stack.
and
Dynamic.
dynamically allocated
Variables stored on the heap.
on the heap. Okay? So, and then we did, what else, what did we do next? Information representation?
We have the data flow one, or whatever.
Oh, the 4 parts of a computer.
Yeah.
Oh, yes.
So what are the 4?
Input, CPU,
Input,
memory, output.
CPU, memory, output device, and they're connected with a bus. And what's the bus?
With the wires.
You're right. That's his question. Everybody has their own. Okay, and then,
Do you guys know the prefix chart?
What?
say it again?
The prefix chart?
What's the prefix chart?
Like
Petaterra, giga, mega.
Petaterra, yeah.
Kilo.
Oh, yeah, you need to know, yeah,
X and
sure. Kilo, mega, how does it go? Kilo, mega, giga,
Tera, peta,
tera, yeah.
terapet.
Yeah.
Tera.
And what's, okay, and 1,000 is actually, a computer science kilo is 2 to the what?
1024.
2 to the 10.
It's 2 to the 10. And so a computer science mega is what?
2 to the 20.
And a computer science giga
2 to the 30.
is 2 to the 30th. Is everybody good on that? And then we did information representation, is that right?
Those keywords don't ring any bells.
Well, information representation was how information is stored in memory.
Well, we did function calls.
Oh, function calls, yes, we did do function calls. Ooh, let's remember that one.
Oh dear.
So what happens whenever you call a function? First, yeah, and in what order?
On the stack.
On the runtime stack.
Push storage for the return value.
Storage for the return value,
Push parameters.
then the parameters,
The return address.
Return
then the return address,
Yeah, local variables.
and then storage for the local variables.
And then returning from the function.
Is the opposite.
It's the opposite.
Yeah.
And then for a void function, you do everything
No return value.
except for,
storage for the return value.
right, because void is, there is no return value. And we drew some stack frames.
Yeah.
Okay?
And then we got into binary.
Then we got into information representation, which in the computer is stored in binary.
Right.
And so
Instructions that
we did, yeah, at the ISA 3 level, okay? And so we did unsigned integers. So for a given, you know, for a given number of bits in a memory cell or in a storage cell, you need to know how to do the range of values. Okay? And then we did, and know how to add and what the carry bit is. And then the, for signed quantities, signed integers, what did we have? What?
The twos.
The two's complement binary notation. And what's the, so you need to know how to, for a given number of bits in a storage cell, you need to know what the range of values that can be stored in binary and in hex. And we need to know how to convert from one to the other, right? So, I mean, you know, we don't have to do examples of these. Okay, so, and then what else? We need to know how to add. And we need to know when we add, we need to know what the what the NZVC bits, each one of those bits is when you do the addition. And then we did arithmetic shift left and arithmetic shift right.
Rotates.
We did the rotates.
Oh, look, there's the technology penis.
Are we good?
I really need to look at these NZC.
The NZVC bits? Okay, so I'll definitely, there will be, that's obviously going to be on there. That's too easy of a question to ask.
On knowing.
The
Yeah.
RTL.
And then RTL is the register transfer language. Okay. You know, I can't imagine what kind of a question I'd ask you, an RTL question, you know. I don't, yeah, I don't,
So don't
you
worry
know.
about it.
Well, I mean,
No.
you know what it is, but,
We don't need to test on it. 'cause
Right.
it's very
We don't need.
okay, so, and let me see, what did we do next?
Then hexadecimal.
Oh yeah, hexadecimal is actually just an abbreviation for binary. So here's the thing, when I give you all these tables, I will not give you the table that has, you know, the hex characters with the binary. But on the other hand, that information is already in the ASCII table, if you think about it, which you will have.
Okay.
In other words, what is A?
42?
I don't know.
Or 60?
No, I mean in binary. The hex digit A stands for what,
Oh, 10.
well, but in binary,
Oh,
1010.
1010, yeah. So, you know, and then B, C, D, but you can, that information is actually in the, it's actually, you can know what letter corresponds to what bit pattern by looking at the ASCII chart. Or you can just do it in the margin of your paper, you just count up to 15. Make your own little chart in the margin of your paper. And then the ASCII chart, yeah, so you will have the ASCII chart and the
instructions.
and the instruction chart, yeah, the inside front cover and the inside back cover. And then you'll also have a copy of the memory map of the computer,
What about the,
So we won't
like
need to-
addressing modes?
and you'll have the tables, you'll have all those tables
For the addressing
for the addressing modes. So, and I definitely will, I mean, you just know there's going to be, I'll give you an assembly language program, and you're going to have to fill out the column, the object code column for all of for any instruction and for any of the dot commands that we studied. All right, so, and it's easy for you to, you know, quiz yourself on that because you've got you got the PEP 8 thing that,
Test it.
you know. Yeah? And then, so after we did all those instructions, we learned about the von Neumann execution cycle. The steps are
Fetch, decode.
Decode.
decode,
Increment,
increment,
execute.
execute, repeat. Fetch, decode, increment, execute, repeat. And,
The CPU.
oh yeah, now I won't give you a picture of the CPU. That's the one thing that'll be missing. So let's review what yeah, in other words, what's inside the CPU? The first thing was what? It's a nibble.
Status bits.
It's a nibble
A nibble for the bit.
for the bits. Yeah, status bits, NZVC, and then what?
Accumulator.
Accumulator,
Index register.
index register,
Program counter.
program counter,
Stack pointer.
stack pointer,
Instruction
stack
register.
pointer, and instruction register. And what does and whenever you do fetch in the von Neumann cycle, what's it doing?
It fetches
From main
Program.
memory.
From where? From memory, but at what address?
program count. Or program counter.
The program counter contains the address in memory of where to fetch from. And then it decodes the instruction, and then when it increments, what's it incrementing?
The program counter.
The program counter, either by what or by what? The program counter is incremented either, there's two possibilities. It's either incremented by one if the instruction is
Unary.
unary, or
2. No, 3.
3 if it's not.
Well, it's incremented first once and then.
Well, inside, yeah, at a lower level of abstraction, it's, yeah. It might even be more than that at an even lower level of abstraction. It might even be more complicated at an even lower level of abstraction, which which those of you who are in the computer
That's
systems
absurd.
course will actually see that.
That's all.
Oh, sorry, computer organization.
We are.
Yeah, yeah. Okay, and then we did, and then the other big thing, what's the von Neumann design principle?
That they share the same memory.
What shares?
Data and
Data.
instructions.
Data and instructions share the same memory, and as a result of that, what can the program do? Because of this von Neumann design principle, what can a program
Change
do?
itself.
It can modify itself.
Okay. Yeah.
And so there might be a sneaky program, a self-modifying program that or there might be something where it tries to execute something that was put in there as data, or there could be all kinds of sneaky things. So you need to know how to translate, and then given or you might, I might ask you to write a short program, assembly language program to do something, I don't know.
Oh boy.
Okay? So that's about it.
Do we have to know, like, all of this? We won't be given, like, what each instruction does. We just have to know all of that.
Right. Yeah, that's a good point, because
There's a lot.
you really need to know the difference between load and load byte and store byte. We did you might want to review your homework assignment on that,
Character output.
and character output and character and decimal input. The only thing, the only description that you will have is the one that's on the inside front cover.
Right.
That's the description that you'll have.
Very short description.
Yeah. So you need to know how those work.
Okay.
Yeah? Okay? All right. Now, if you want to, you can put a mental barrier here so that everything that we're going to do from now on is not going to be on the exam on Thursday, but you will need to know this information for doing the homework on Monday. It's actually a pretty big topic, but I think you'll like it. Okay, so let's begin by looking at figure 5.12, this program in figure 5.12. Now, check it out, you guys. Actually, I think this is the program that we did a demo on, and we modified it to leave off. I think this is the one where we left off the sentinel of the dot and the dot ASCII, and it printed out that 3-1 as deci as a 1, and we analyzed it to death, right? Now look, you guys, the programmer who wrote this program, the first thing that she had to do was, at the top, she had to say branch 0x someplace. Now right now it's 0x000D, right? But how do we calculate that 000D? What do we have to do?
Count the number of
We have to count how many bytes are in the dot block, then count how many bytes are in the dot ASCII, and then by counting all that stuff up, figuring out that that deci, that first instruction, is going to be at address 000D. Are you with me?
Yes.
Okay. What's the fundamental question of computer
What can
science?
be
What can be
automated?
automated?
So what do you suppose?
We can count the number of bytes,
Well, could that be automated?
I suppose.
Could that counting from where the first one starts,
If we told
Be-
it something to look for, I suppose.
well, what would we have to do? If you were to write a program to automate that? Yeah, what do you mean, is something to look for?
Oh, and it has to know when the first actual instruction is.
Yeah, so here's what we would have to do. In order to automate that counting, what we would have to do is we would have to have a way to put like something, it's called a symbol. It's called an assembly language symbol. What we're going to do is we're going to have what's called a symbol, and we're going to stick it in front of the deci instruction. Are you with me? And then when we say branch to this, whatever this address is, then what it will generate is the address of where that symbol is.
Plus one.
No, it will be the address of where that symbol is. Do you see what I'm saying? In other words, and here's what a symbol is. A symbol, so our symbol will be this. Our symbol will be, we'll just make up it, and we'll just say main, and we'll put a colon after it. So here's what, so what we're talking about now is a way to automate the counting so that we don't have to count ourselves. We'll have the assembler do the counting for us. Do you see what I mean? So what we'll do is we will define a symbol. All symbols, the definition of a symbol in assembly language, it's an identifier. Programmer makes up this identifier, and then you put a colon after it. And then the assembler recognizes any identifier with a colon after it at the beginning of the line as a symbol. Are you with me? And then what it does is it can count, starting at 0000, it can count all the instructions that are from the beginning to this point, and so it will figure out what that address is. Do you see what I mean? And then what you do is, instead of saying branch to 0x000D, what do you say?
Branch to
You
main.
say branch to main. And the value of main is the address. So look.
Does main not get loaded into the memory at that point then?
Well, yeah, let's talk about exactly what happens in a minute. Okay, so that's the concept of a symbol. A symbol is defined by an identifier followed by a colon at the start of a statement. So you see, that's what defines it. And then the value of a symbol is the address of the object code generated by the statement. Do you see what I mean? It's the address of the object code. So here's that program written with symbols in figure 515. Now look at this, you guys. Look how slick this is. Now what does the programmer do? Instead of saying branch to 0x000, you can just say what? Branch to main. And then what do? You put main colon in front of the one that you want that to be. Are you with me? And then what the compiler does is it counts, because the compiler, the assembler. So what does the assembler do? Is it counts how many bytes are in the branch. So that's 3 bytes for the branch, 2 bytes for the dot block 2. Are you with me? And then it counts how many characters are in the ASCII string. It counts all that up. And then that is the address, that is the value that it gives to main. Are you with me?
Okay.
Does everybody see how that works? So not only does this figure 515 show the assembler listing, it also shows the symbol table. And there's not, because there's more than one symbol here. Not only is there a symbol called main, but now, whenever we did decimal input, what did we do decimal input? What did we have to give after the decimal input? We said decimal input 000 or we said decimal input 0003, right? Well, we can do the same thing for decimal input, yeah? What we can do is we can just make up a symbol name, we'll call it num, colon, and we'll stick it right in front of the dot block.
It's so much better.
Still direct addressing? Direct to num?
What's to that location?
Well, if you look at the object code that's generated here, it's the exact same as the object code that was generated before.
Wow.
Are you with me? Does everybody see how that works? So now what happens is the num, so whenever you say deci num, well, what value does num, here on the symbol table, what value does num have? 0003 hex, right? So whenever you says deci num, it's deci, see the object code that's generated? It's 310003. 31 for the instruction specifier, 0003 for the operand specifier, right? Is that cool? And then whenever we did stro, remember how we did stro? Well, we'll just call it MSG for message, a little short, yeah, a little symbol for message. And that's the address of the first byte of the .ASCII, which is at 0005. So we do stro message, comma direct. And now, boom, all that's automated. I thought you'd like it. And so if you look at the object code is the exact same object code that was before. Only thing now is we have this advantage of symbols. And then the symbol, and so the main idea here is, what is the value of a symbol? The value of a symbol is the what?
Address.
It's the address of the object code generated by the statement. That's what the value of a symbol is.
Which statement?
Well, the statement that you put it in front of.
Okay.
See, so for example here, the value of main is the value of main is 000D, because that's where the 31 is stored.
Okay.
The value of the symbol num is 0003, because that's the address of the first byte generated by the .block command. And the value of MSG, of the MSG symbol, is 0005, because that's the address of the first byte generated by the .ASCII command.
I have a question. Say we were to put, we'll say under the decimal output, if we put num and then did immediate, would it?
What would come
would it
out?
output the address that num is at?
Yeah.
No, it would the object code that it would generate would be, instead of being 390003, it would be 380003, because it would be immediate addressing. And the thing that would come out would be 03.
Right, because that's where num is. Okay.
Well, I mean, it's
What num?
The
It's
address,
what
the
num-
value of num.
it's the value. Yeah. Well, if you look at the object code that's generated, it would.
Okay.
It's kind of better to think of it in terms. You pretend like you're the CPU and you're just fetching and decoding and executing,
Right.
and look at the object code. Don't get. Yeah, some really interesting things can happen when we when we do these symbols, and you always have to keep in mind, what does the object code. I mean, it's just a shorthand to help us not have to count bytes to know where things are going to be in the program. Is everybody clear? And so this program here, the next slide, shows, it's the exact same object code, so it's the exact same thing happens. So I don't think I'll bother to demo that right now. We'll demo another one in a minute. Okay? Is everybody clear on that? Now, you always have to remember that these symbols, I mean, the assembler does the translation, and after it does the translation, what happens at execution time is separate from what happens at translation time. So you can do really funny things with symbols. So watch this. Suppose you write a program like this. Suppose we have this symbol, this. And the statement is deso this deso this direct stop dot end.
be 0.
Wait a second.
Nope.
Would it be a decimal output of the bit code for deso?
Yes.
It's like, what is it,
Yeah.
338?
Yeah, can you figure this out? Can you figure this? Can you predict this? A little pop quiz here. Could you predict this?
I don't remember what.
Well,
Deso.
deso, yeah, let's figure out what deso is. This would be a good
It's 3.8 because it's direct instead of 3.9.
3.9 is direct.
oh, so is it,
Oh, 3.9 is.
3.9 is direct. So this would be 3.9, so the object code would be what? 390000.
We need to know where it is in memory.
That's what it would be, right?
Yeah.
And then stop would be 00, and that would stop, right?
Yeah.
So this would do, so what would this do? This would do a decimal output from address 0000.
Which is a word. It has to
Yes, so what will it, so what is the number that it will do the deso on?
0011. Oh, sorry.
Oh, yeah, it's 3900. So what were you going to say? So this is what?
0011.
0011
1001.
1001 0000. So we could either do this in binary, or we could do it in, this is the ones, since it's positive, right, there's no 1 in the sign bit, we could do 1s, 16s,
So 9 times 16 squared.
9 times 16 squared plus 3 times 16 cubed, right? So it'd be 9. Yeah, somebody have a calculator? Let's see if we can predict this. 9 times 16 squared plus 3 times 16 cubed.
14,592.
14, say it again.
14,592.
14,592. Okay, are you ready? Drum roll.
Well done.
14,592. See? So you have to remember, what happened to my pen? So you have to remember that that all these rules for symbols and the assembler thing, it all goes back to binary, and then in binary it's the von Neumann cycle. And you might think it does weird things, but to understand how the von Neumann cycle works, you have to be able to, predict what the output would be in an unusual situation like that. Okay, so now we're going to do, we're going to start on a long journey that we will be on for the rest of the semester. What we want to do now is we want to see how a C++ program gets translated. Now, what kind of translation have we been learning up until this point? We've been translating from what level to what level? Assembly 5 to ISA 3. Are you with me? Assembly 5 to ISA 3. And that translation is the translation project that you're going to do. You're going to automate that.
Right.
Okay? But now you guys, what's going to we basically know pretty much all there is to know about that.
Pretty much.
That's pretty, it's pretty straightforward. There's not a whole lot of rules, but you can do it. You understand how to do that now, and so it'd be pretty straightforward to write a program to do that, to automate it. But now, this next, it's a little bit higher jump, a little bit higher reach, because what level is C++ at?
6.
That's at level 6. So now we're not translating from level 5 to level 3. We're translating here on figure 5.17, what? From level 6 to level 3.
Wait, 6 to 5.
Well, yeah, okay, so now that's a good question. So the question is, when you compile a program, when you write a program in C++ and compile it, what does it get compiled to?
5.
ultimately, it has to get compiled to what?
To 3.
To 3. Because in order for it to run, it has to be in machine language.
Right.
But that is not the only possibility. It's also possible to have it compile from level 5 to level, from level 6
Directly level.
to level 5. But then if you do that, what do you have to do after that? Assemble it from 5 to 3. And that's not uncommon. I mean, it's actually possible to do that. In fact, it's not uncommon at all.
In fact, it's more common.
Well, I mean, I'm not sure actually in practice which is more common.
Does that just depend on what compiler you use, or?
Yeah, and it also depends on what you want to do, because here's the thing. Fewer and fewer people these days program directly in assembly language, because the compiler technology has been around for so long that they've gotten really good at translating from a high-level language, a high-order language, HOL6, so that the object code will perform well. But there are times when the best human assembler, the best human compiler can actually write code that will execute more efficiently and faster than even the best compiler can do. So if you want to squeeze the ultimate performance out of your program, you could do what? You could write the whole program in
Machine code.
in machine code. Well, assembly language, you're not really saving anything by writing a machine code compared to assembly language, because one assembly language statement is one machine code statement. Are you with me?
Right.
So you're not sacrificing performance when you write in machine code. I mean, you're not sacrificing performance when you write in assembly language as opposed to writing in machine code. But you could be sacrificing performance when you write in higher language compared to writing in assembly language. As a matter of fact, in the early days, I have a story to tell you. In the early days, there was a company, and they put out a this is when word processors were brand new, all right? And they bragged in their advertisement that their word processor was written in assembly language, and it was fast. Because, back in those days when computers were really, really slow, they wanted to get the most performance out of it as possible. And those guys, they had the fastest word processor on the market. And for a while, they had, their product did very, very well. But unfortunately, can you imagine having to write all your programs in assembly language? What would be the problem of writing your programs in assembly? If it's fast, if the programs run faster, if you write them in assembly language, why doesn't everybody write in assembly language?
It takes forever.
Yeah, it would take forever to program. And when the program gets bigger, the bigger the program gets, then what problem do you have?
And then it's really.
Then it's really hard to maintain it, because it's all, So it becomes expensive. And so over time, what happened is the computers got fast enough where the benefit of having it run faster was outweighed by the benefit of being able to maintain it, you see, because it'd be too expensive. You'd have to hire teams and teams of programmers, and it'd all be tedious. Okay, but there are still occasions whenever you want to take part of your program. Actually, here, let me optimize that part of the program. And here's let me write down a principle here. This is a rule of thumb. 10% of program statements of program statements in a program, in a typical program, 10% of program statements in a program are responsible for 90% of the execution time. Now, whether it's 10 and 90 or some other number is I don't know what the exact, I mean, nobody knows, well, somebody knows. I mean, in a typical program, studies have been done, and it's not exactly 10, it's not exactly 90, but you get the point. What's the point? You know, when you write a big program, most of the execution is in the what? Is in the loops. And there could be a huge part of the program that's based on just the user interface, you know, da-da-da-da. But then, you know, if it's really compute intensive, then a small part. So, which brings us back to translating from level 6 to level 5 as opposed to level 6 to level 3. How does this, what does this have, can you see the connection between this and this?
If we can write those statements in assembly language.
It doesn't pay to write the whole thing in assembly language to speed it up when just a small part of the program is responsible for most of the execution time. So what you would do is you'd write the whole application in a higher order language, and then do what? Instead of doing A, translating the whole, you do it to B. And then what do you do? So now you have this whole program, and it's written in a higher order language, and now it's translated all into assembly language. But now, so now what do? You just take the what?
Assembly.
Well, you just take the little functions, you know, the functions that are responsible in assembly language, and then you can tweak those by hand and get better performance out of it, and let the compiler take care of the stuff that's not so critical in the bottleneck, in the performance bottleneck. Are you with me? And that's quite common. So that's the way assembly language programming is done today, for the most part. You let the compiler do the whole thing, and if you ever want to get down to the assembly level, you just get down to the part of it that you really need the performance. Are you with me? So now what we're going to do from here on out, our big journey is going to be how the compiler translates from level 6. And what we're going to do is we are going to use, even though in practice sometimes it's done as in A, going from 6 to 3, we are going to go from level 6 to level 5. Because level 5 is we can think in symbols and stuff like that. You know, it's, all right? So the first program that we're going to translate is we're going to see how a C++ program that has cout in it is translated. So obviously, if you, and so how does the cout work in C++? You know, it outputs. You say cout, blah, 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 blah. And what kinds of things can you output? You can output strings, you can output characters, you can output integers. So what's the rule for translating cout? You translate a string output with stro. You translate a character output with charo. You translate an integer output with deso. All right. So here is our first program. And now what we will have is, our job now is, given this C++ program, which is what in this figure 5.18. Pound include IO stream, using namespace std, int main, cout love, all you need is love, and then, Valentine's Day, appropriate for Valentine's Day, and then return 0. Okay? Now, here's the thing, you guys. How do you translate the pound include? Well, we're going to ignore how that, because see, that pound include is using the libraries, you know, and stuff like that. Okay, so, and then using namespace std, we're going to ignore that. And the other thing that we're going to ignore is, do you remember how you remember how main is int and it returns 0? Okay, we're going to ignore that. So in a real life application, that stuff wouldn't be ignored, but we're going to ignore it, just to keep things simple. Yeah? So the only thing that we have to translate here is cout love. Okay? So obviously, so how do we do it? And here's the other thing we're going to do. From now on, we're going to put all of our string constants at the bottom instead of at the top. Okay? So how would you translate, so how would the compiler translate that? It would do, well, we have to give the string a symbol, so we just call it MSG. So it's just stro MSG direct. Are you with me? And then what about that end L in the C++ program?
Well, that's character.
That goes to the start of the next line, right?
Yeah.
So how do we translate that?
Character.
Character output, new line, immediate, and then stop. Are you with me? And then the .ASCII is where we have our null terminated string, and so the compiler has to insert that null at the end of E, and then .end. So the output is love. Is everybody clear on that? So here, this next slide is a figure of how the computer runs that are necessary in order to actually run this program. So in part A of figure 5.19, now, what do all programs do? They take input, they process it, and they produce output. So do you see then, what is a compiler? What is the input to a compiler?
Some language.
There it is. Yeah, yeah. It's this like C++ code. It's the program that you write, and then the compiler. Now, if it translates, it could translate straight to level 3 machine, and that's what's happening in part A.
Isn't that fast? Wouldn't that be faster?
Yeah, it could be. Could be.
For
Yeah.
the compiler.
Well, because if you do it to assembly language, then you got to have the assembler
Right.
do another translation. So you're saying would the translation process be faster? It could be, yeah. We're actually going to, when we talk about optimizing versus non-optimizing compilers, there's some interesting question involved in how speed of translation versus speed of execution. So we'll talk about that a lot, actually, in the course of the course. And then in part B, it shows a compiler that translates to machine language. So like I said, so in this case, you have the C++ for the input to the compiler. The output to the compiler is assembly language program as opposed to a machine language program. Yeah? Is that clear? Okay. So now, in figure 5.20, we have, now we have to deal with programs that have variables in them. Okay? Now, so let's think about what a variable is.
Symbol.
Well, whenever you use a variable in C++, how do you declare a global variable in C++?
Static.
Not necessarily static.
It has a type
You give it a type.
You give it a type
A name.
and you give it a name.
and then a value.
Well, you don't have to give it a value. The value could be given to it at
Later.
execution time. Are you with me? Okay, now let's think about global variables. Where are global variables stored? At a fixed location in memory. Okay? And so, here's the correspondence. Because they are at a fixed location in memory,
We can put them,
because they're at a fixed location in memory, that means that
we can store it, right?
if in assembly language, we can use a symbol to have the same name as the variable in the high order language. Do you see what I mean? Are you with me? Because but now there's a difference here because I mean think about what's going on.
The symbol is
The symbol is the address of where of where the value of that variable is going to be stored. That's the connection. Yeah? So here in part A, we see a compiler that translates to machine language, the C++ identifier for a variable name, that corresponds to a memory address of where that's going to be stored. But see, if we instead have it translate to assembly language, then we can use the symbol mechanism in assembly language to make the connection between the variable at the HOL6 level. Are you with me?
So the symbol becomes like its name.
Yeah, we will use the symbol in assembly language for the name. Well, we'll give it the same name as the name of the variable in HOL at the HOL6 level. But really what it is, and it corresponds perfectly, right? Because what is the value of the symbol in assembly language? It's a what?
Address.
It's an address. And so that will be, like for global variables, so that'll be the address of where the symbol is stored, of where the value of the variable is stored. Yeah? So here's the rule. For global variables, we allocate our global variables at a fixed location in memory with dot block. Are you with me? And since they're at a fixed location in memory, how do we access them? How do we access them? With direct addressing. Yeah? Is that clear? So does everybody see here how global variables are, how a compiler would translate a program that has global variables in it? Are you with me? Okay. And now, what's the most common, other than output, what's one of the most common,
Loop
no, even,
assignment.
yeah. One of the most common statements in all of HOL6 languages is usually the assignment statement. So how do we do an assignment statement? Here, what is an example of an assignment statement? Suppose we say like, suppose we say like n gets, 2 times n plus 1.
Oh dear.
Something like this. And then semicolon. So here's an assignment statement in C++, right? So you guys,
Well, you do.
what would you do? What would you have to do? You'd first have to, well, first you do what's on the right-hand side of the assignment statement, right? You figure out that. So what would you have to do here? You have to take the current value of n and do what with it?
Load it.
Load it into the accumulator, and then do what? Multiply it by 2, which you could do with a what?
Do we have an
We
instruction
could
for that?
add-
Multiplying by 2,
By a shift left.
arithmetic shift left.
Yeah.
Or you could add in.
Or you could add it to itself.
Yeah. Okay.
That's actually you could do that. Add it to itself. And then 2n would be in the accumulator. And then what would you do?
Add immediate.
Add immediate 1. And then do what? Store it back into n. So that's the recipe. Oh man, you guys, this is so natural. You guys are good. Look, so here's the recipe for assignment statements. You load the accumulator from the right-hand side of the assignment with an LDA. Okay, LDA is the mnemonic for load accumulator. And then you compute the value of the right-hand side of the assignment if necessary. So here the computation would be times 2 and then plus 1. And then you store to the variable on the left-hand side of the assignment with store accumulator. So here, let's see then if we can figure out how to translate this program.
Okay.
All right, now, we're going to do a lot of these in the future. Okay, so the very first, okay, so we'll go around the room maybe, okay? So the very first statement will be what? The very first statement is always what? Where remember the variables are going to go at the beginnings.
Branch.
Yeah, so the very first will always be what? Branch to main. And then main will be down here somewhere, right? Now, so we ignore the pound include, the using
There's
namespace.
some blocks for variables.
Okay, yeah, so what will,
Block 3, right?
yeah, so this will be, and what's the name of the variable? CH. So here we do CH, we'll make that a symbol.
So would we want to do 2 separate blocks for that? Because
Yes, because we have separate symbol for each one. Then CH would be a what?
block 1.
A dot block 1, and why 1?
Because
Because character is 1 byte. And then what?
Ints.
Int J. So what would that be?
J.
So here we have J,
Block 2.
and this would be dot block 2. Are you with me? And then we'll start our main program. So what do we have here?
Main.
We have main, colon. So now when we branch to main, we'll branch to here, right? And so now what is it? CN, CH, J. So this would be what? No, CN. CN, the character.
Store.
I think store.
No.
No.
Oh, what are the 4 parts of a computer?
Input.
Decimal input?
Hmm?
No, it can't be character input.
Yeah, character input, yeah. Okay. Character input into where? Into CH using what addressing mode? Direct.
Oh,
What
direct
is
CH,
immediate?
yes.
Direct to here. Are we good?
Yeah.
Is this good? Okay, oh, you guys are good. Okay, but now what about the J?
Deci.
That would be deci. into where?
J,
J, addressing mode?
direct.
Direct. Good. Is everybody clear? And now how do we do J plus gets 5?
J gets J plus 5.
That's the same as J gets J plus 5. So what do we have to do? So we have to load accumulator, the what?
Accumulator, J direct.
Load accumulator, J direct, and then
Add a.
add accumulator, good.
5 immediate.
5 immediate. Oh,
No
And
store.
then store.
excellent,
Store.
excellente.
Store.
Store accumulator, J.
Store accumulator,
Yeah.
J.
J direct. Yeah? And imagine the compiler is doing this. The compiler takes that and it does this,
That's
automated.
pretty impressive.
Yeah, but that's what compilers do. And now what? CH++. So what is that?
Do the load.
Is that going to add the ASCII value?
Yeah.
Yeah. That's a legal C++ program. Okay, so load accumulator,
CH,
CH
direct,
direct,
Redo
add
add
one.
accumulator
1 immediate.
1 immediate. Oh man, you guys are on a roll. And then what? Store accumulator, CH what?
Direct.
Direct.
Direct. Okay. Keep on trucking.
Character out,
And now Caro
CH direct.
CH direct.
Character out,
Deso.
slash n,
Well, the inline.
slash n. Yeah.
You see the inline, so we have to do, how's that?
Character out for dash n.
Yes.
Slash n.
Caro, quote, bash n, immediate. And then what?
Des out,
Deso,
J direct.
J direct.
Character out, dash n immediate.
And then Caro, bash n, immediate.
Stop. Dot n.
And then stop, dot end. Huh.
That's not bad.
No. Okay, drum roll, are you ready? Did we do it right?
Yes. Looks like it.
Check it. Let's check our work.
Oh, what about load byte?
Ooh, we made a mistake.
Character.
Oh, we made a mistake. We didn't do it correct.
Maybe load accumulator.
Yeah, this character is a single byte. Well, we have to correct our.
Load byte A.
And it just store.
Oh, where? Here, right?
Yep. And store byte.
Yeah, this should be LDBYTE, load byte accumulator.
Did you know we got it wrong as we were doing it?
I forgot. And then add accumulator 1, and then this should be what? Store byte. Now is it right?
Yeah.
Ooh, and that's, I tell you,
Very important.
yeah, that happens, although that frequently has a common mistake. I should have remembered that.
In fact, yeah, we would have grabbed the character and then the first byte.
Yeah, it would not have worked.
Been very strange.
Okay? So anyway, on your homework for Monday, you have some translations to do. There's a few more translation techniques we have to learn for your homework on Monday, but I think we've covered most of it. Okay?
Great.
Good deal. So see you for the exam on Thursday and then on Monday. All right.